absolutely fantastic turnout and final performance. I mean, I don't know, what have we got, 300 plus in here or something? That's great. You still got smiles on your face. It's been a long day. For me personally, I'm seeing a transition in the debate we're having. We're moving from, I guess what I would have seen 7 or 8 years ago, we was talking about maintenance and how many magic maintenance systems, computers and bar charts and graphs we could generate, into a totally new era. And the debate that we had here this afternoon about, well, what do we call it? I don't know, asset management, productivity, effectiveness, or whatever. It's certainly a very healthy start in the culture to move forward. And I did also like the references to the journey that we have all made in our industries in safety management. 10 to 15 years ago, you know, it was hard to get a CEO to really come to terms with that whole concept. And today it's the first or second word out of their mouths whenever they talk. So we can make progress, and we will, and it's good to see that language starting to change. Let's move right along. Thank you for all the atmosphere, the enthusiasm and the buzz that you have created out there today. It really feels like a lively place out there in Exhibition Center. After we have finished here this afternoon, we will have drinks and networking. It's party time out there, guys. And we should please also thank TWM for their kind sponsorship of the event afterwards. So, round of applause for TWM, please. A couple of final administrative points. Hands up all those who completed their assessments. Hey, I should say this only once, more today. All right. Tomorrow there's also an interesting thing over lunch in, I think it's the Blue Room. We have a special lunch and learn session. So that is available to you. It's going to be led by Larry Olson from Nexus Global on improving your asset integrity and equipment reliability. So grab some lunch tomorrow and make your way to Blue Track for that session. All right, one of the highlights of the Mainstream Conference, amongst others, is always the final session on day one. It is always electric. It's always something that we learn something different, we get a different perspective, and we always have the best presenter we possibly can to do that. There's only one question I've got for you. Did anybody actually bring a toothbrush with them? Nobody brought a toothbrush. Our next speaker did. His name is Ed Van Cise. Ed is a space station manager. I'll give him his real job title. Ed's been involved with International Space Station operations since the first piece, I think that's a technical term for something you throw around the orbit world, was launched in 1998. So he's worked his way up through various consoles in mission control, and Ed was selected as a NASA flight director in 2009. With call sign Carbon Flight, Ed has been a leader in space station flight control for more than 6 years. Ed is now the International Space Station Flight Director for NASA administration. I'd like you to please welcome Ed while he talks to us about how to use a toothbrush to repair a space station. Hold tight.
Oh, how's that for an intro? I think that means that when you do your evaluation, so I get the final say, right? Don't include the proximity or the timing with which I keep you from drinks in part of that evaluation. It's always hard to be the last speaker, but we'll try to get you out of here on time and share a little bit as well. So before I just jump into the slides, I think maybe the first thing to do is go over a little bit more in detail on what a flight director does, just so you know my background and where I'm coming from, and then also try to match up language. So we're kind of talking about using the same terminology. So what does a flight director do? Flight director works in mission control and is the lead of the team of flight controllers working, in my case, the space station mission. You've got it's very similar to the control rooms that you all are familiar with. You've got a bunch of consoles in the room. We've got different people responsible for various subsystems on a spacecraft, the day's plan. We talked about dynamic scheduling. We pretty much live in the world of replanning today. And then we also do strategic planning. So we actually do today's plan, tomorrow's plan, 3 days out, 7 days out, 3 weeks out is how we do planning and mission control. So you have teams that do all of that. All that information is integrated not only amongst the consoles, but then also with our international partners, because it is the International Space Station. We have 5 flight control rooms supporting around the world. And then for each of those rooms, that information goes to the flight director. The flight director makes the decisions to implement the mission. My responsibility as the Houston flight director is not only to manage the US segment of the space station, but we also have the primary lead role. So we're the lead flight control room for the International Space Station. So Houston Flight is the overall authority. There is no higher authority when it comes to executing the mission. Even the crew works for the flight director, except for cases when having the crew commander making decisions based on what they see will help keep them safe. So that kind of sets the stage, just what my title is and where I come from. A little bit on terminology, talking about asset management. So we don't necessarily do space station for profit, but we do have an end product that we're trying to accomplish, and that would be groundbreaking scientific research that can only be done off planet. And so that's our bottom line. So that's our cash flow, if you will. And then we have a vast number of assets that we utilize to make that happen. Obviously, you've got the space station, but then you've got a number of rockets and capsules and facilities that support all of those things. And so all of that folds into the asset space, if you will. So we'll talk a little bit about my baby. I actually covered most of this already, but key thing to point out, if you're not aware, is that the space station has been occupied by at least 2 people, currently 6 people, since the year 2000. So I have 11 and 12-year-old children. For as long as they've been alive, human beings have been spacefaring. Human beings have been a spacefaring species. So you know, if you have kids or know anybody that's born after November of 2000, they've never existed when humans have not been off planet. So we really are living in that era. There are quite a number of space flights that are required to support the space station. Now, this number says over 170. It's well over 180 now from all around the world. So it is definitely an international collaboration. So how big is my spacecraft? It's about the size of a football or a soccer pitch. Each of those 8 solar arrays is about the size of a basketball court, 430,000 kilos, about the size of an American 5-bedroom house. Creates enough power, solar power, to power about 40 homes. Fly at an altitude of 415 kilometers, going 28,000 kph. So you cover just under 8 kilometers every second. That means you get to see 16 sunrises and 16 sunsets every day. Yesterday, I get my dates right, but I guess it was a couple days ago now, we just launched 3 people from Kazakhstan up to the space station. They went from 0 to being at the space station in just about 6 hours. And that brought us back up to a crew of 6. The crew stay on board for 6 months at a time. So obviously there's a lot of logistics that are required to support 6 people on a space station on a continual basis for over 15 years. And because we're in low Earth orbit, we have the luxury of being close enough to Earth that we can have a steady supply of cargo ships coming and going. Space station is as much a spaceport as it is a research facility. But just like your industries are hard and complex and remote and challenging and have things break down, obviously so does the space station. And getting cargo ships off the ground is not an easy task. And you can have anything from weather to very complex breakdowns in equipment stop you from getting a launch off on time. And of course, it's a risky business too. And because it is so complex, sometimes you get the unexpected, rapid, unplanned disassembly. And we plan for that, right? You can't assume 100% success rate. So we do what we call skip cycle planning so that we have enough critical consumables on board to keep the crew alive for 4 to 6 months, so we can skip 1 cargo ship. So I don't want to say it's not a big deal because that's how our science gets up there, and clothes and things like that too. But we can survive 1 loss. Unfortunately, last year was not the best year for us. So in October of 14, we lost 2,200 kilos when this happened.
5, 4, 3, 2, 1. And we have liftoff of Antares, the 3 missions that brings Cygnus on its 3rd main engine's at 108%.
Avionics power nominal.
Wait for it.
And launch team, be advised, stay at your consoles. Everyone in the LCC, maintain your positions in your consoles. In the LCC, maintain positions at your console.
And if that wasn't installed enough, but as you saw, it actually came back down on top of its launch pad and took out a lot of the launch pad facilities as well. So this is an Orbital Sciences vehicle. They have returned to flight. We're actually about to launch the next Orbital Sciences cargo ship this week. But it's launching from Cape Canaveral on an Atlas V. Their spacecraft is flexible enough they can use multiple launchers. So while Antares, which is their launch vehicle, is getting recertified, they're flying on an Atlas. But later this summer, they'll fly again on their Antares. But it was, a bad day, but not that bad because the reliable Russian Progress was up next. We've never had an issue with the Progress. They can bring up a lot of cargo and propellant for the space station. Until in April of last year, this happened with 2,400 kilos.
The camera on the Progress was activated and showed a rather significant rotational spinning motion on the Progress. You can see the Earth spinning from the television camera's point of view. And the Russians also reported, and it was confirmed by the visiting vehicle officer here in the flight control room.
Yeah, it's not supposed to do that. So what happened with that one is the third stage of their rocket had a malfunction right around the time the Progress separated from the upper stage, and it actually ejected the upper stage into a higher than planned orbit and destroyed some of the components on the Progress vehicle, resulting in the unusable spin that you saw, and then it had an uncontrolled reentry and we lost that cargo. And then we still weathered that storm until the SpaceX cargo flight was supposed to come up in June of 15, had 1,900 kilos, but also had one of 2 international docking adapters that are critical to be able to do the commercial crew program that we're working on to, again, launch U.S. Vehicles from the U.S. soil up into low Earth orbit, dock to the space station. So we definitely needed that docking adapter, but then this happened.
Impact chill has begun. T plus 2 minutes. Altitude 32 kilometers. Speed 1 kilometer per second. Downrange distance 13 kilometers.
Your rocket is not supposed to disappear. Yeah, it went all over the Atlantic Ocean. So some things to point out, right? Because I'm sure this applies to your industry too. You want to have redundancy in your critical equipment. You want to have dissimilar redundancy, and we did. We've got, in this case, 3 different launch providers, 3 different ways of getting cargo to orbit. You could tell all 3 of them had completely different failure modes. So it was, everything stacked up against us, unfortunately, during that time frame. We did have enough supplies on orbit to not only keep the crew going, but also to do some very useful and good science. But we were stretched pretty much up to the limit, and the next vehicle really needed to get to the space station, or we would have to start talking about bringing some of the crew home. But the Japanese cargo ship, the HTV, did successfully make it to the space station, and we're back on a good track. SpaceX is actually set to return to flight on April 8th. So everything's going according to plan now, but that skip cycle planning and our logistics, if we hadn't been doing that, then we certainly would have had to bring the crew home after those 3 issues. So we'll talk a little bit about the workhorse of space station assembly, and that's the Space Shuttle. So this is an incredibly amazing vehicle, as I'm sure you're aware. It could carry up to 7 people. It had its own robot arm. It had its own airlock, and it had by far and away the best upmass capability of any space transportation system that we've ever devised, including those that are in operation now. What's also amazing is it could also bring a tremendous amount of cargo home. So what you're seeing in this video, it's doing a somersault underneath the space station. I'm sure you're aware of the Columbia tragedy when we lost Columbia due to foam impacting the heat shield of the shuttle. Part of return to flight, we implemented this somersault underneath the space station to take high-resolution photography to make sure the heat shield was in good shape. But you can also get a peek inside the payload bay and see it's actually a cargo module for the space station that's bringing up a tremendous amount of supplies. Space Shuttle was the design cargo ferry for the space station. From the very beginning, the sole purpose of Space Shuttle was to service a space station. And the sole means and method for assembling and then maintaining the space station is through use of the Space Shuttle. Never until Columbia happened was there any real thought given to the fact that what if Shuttle stopped flying? So this morning we talked about disruptive change from the industry, right? And how a lot of times that disruptive change can be forced upon an industry from an outside party, but you really want to have that come from within. Well, that didn't happen when it came to shuttle retirement. There was no really any discussion about shuttle may eventually stop flying. We're just going to fly it for forever. And so they really hadn't put any thought into how we might get cargo, especially very large cargo, up to the space station. And Columbia happened. We realized that Space Shuttle as a system was not nearly as safe as we really thought it was, and we needed to get out of the business of flying people and cargo in the same rocket and then sticking all of the people on the side of a rocket, because that's really not the safest way to go about doing things. So we went into a phase of retiring the Space Shuttle, and that's when we realized we needed to have other means of getting cargo up there. So we very quickly had a paradigm shift out from underneath us. We were forced into this disruptive change. There were a few years of uncertainty on what we would do, and then we came up with the commercial cargo program, and so now we have those multiple vehicles that we just talked about to get cargo up to the space station. So it's been a success for us, but it's not one that we were planning for. So lesson for you, really I'm just repeating what was said in the opening keynote this morning. If you can think ahead as possible paradigm shifts, and even implement them from within your organization, then you are ahead of the game as far as them being thrust upon you. So that's one way we plan for failures, but also inside mission control, our job as operators is to always think about what could break and what we're going to do about it. I mentioned the fact that Space Station is supported by multiple control centers around the world. Almost all of them only go through Houston as far as communicating with the space station, and then Russia actually has a direct line of sight. Space Station is a software-operated vehicle controlled by the ground. The astronauts don't fly it, and we send between 7,000 and 12,000 commands to the space station through Houston every day to keep it running. This is a look inside of Flight Control Room 1, or FICR 1 as we call it. Again, it looks very similar to photos that you've been seeing all day of what people's various control centers look like. This is a special day for me, special picture for me. In this view here is the Japanese cargo vehicle. It's HTV number 4. And this is what mission control looks like on one of our busiest days. We're about ready to have the astronauts take the robot arm on the space station, reach out to grab onto the 20-ton HTV, separated by about 10 meters from the space station, both flying at 28,000 kph. So it's a busy day, very controlled, very methodical way of doing things. And it's one of my favorites because that guy right there is me. So that was what this HTV-4 was my mission. And I'll talk a little bit more about HTV-4 tomorrow if you're not enchanted with the other topics that are being discussed. So sometimes you plan for failures by flying up spare parts, and sometimes you plan for failures reactively, like we've been talking about today, and as you well know. So what I want to do a little bit of a case study on, and we'll get to the toothbrush, is on another issue that I was involved with in the fall of 2011, and that's with the main bus switching unit. We're NASA, so we use acronyms, so I'll talk about it as the MBSU. And it's basically just a big hunk of a box that sits on the space station. You really don't think too much about it. It's a solid state relays inside, and every once in a while you need to reroute where power's going, and so you open and close switches. You don't really interact with it a whole lot, but you've got 8 power channels on the space station and 4 MBSUs. So 2 power channels come into each, and then we just move the power around. And we get a lot of our redundancy for space station power by manipulating those switches inside the MBSU. It's a dumb box, except for the fact that it's actually talking to a computer when it needs to open or close its switches. And in the fall of 2011, the computer stopped being able to communicate with the MBSU. The switches stayed in their last state, so that wasn't a problem, but we actually had some missions coming up where we needed to move the power around, so we needed to regain that capability. We have the capability to do a contingency spacewalk. Uh-oh, I think I broke this. There we go, okay. We can do contingency spacewalks, but we really don't like to. We like to do them more in a planned out fashion. And the engineers that looked at the problem said, you know, we don't have to go fix this right away. We've got time. And so we took about 12 months to go plan the spacewalk. That's our normal template. So if you want to go do a spacewalk, you want to optimize the procedures and the timelines and the crew training, you take 12 months to go plan it. Every time on TV when you see somebody throw on a spacesuit and hop outside, that doesn't happen in real life. And honestly, they'll probably be dead in a few minutes from getting the bends because of the pressure difference. But movies are fun. Real life is boring sometimes, right? So we targeted a spacewalk in the fall of 2012. Just to help you familiarize yourself with the space station, this is the front of my vehicle. In red is the work site we needed to go to. It's right on the center line of the space station. This right here is the airlock, and the hatch is right at the bottom. So when you open the hatch, you're ready to come outside. You're actually looking straight down at Earth. So the first step is quite a doozy. The astronauts actually prefer it when they egress or they go outside at night, because then it's not as big of a fall, if you will. So they just needed to come from the airlock up to this work site here. This is MBSU number 1, and our spare MBSU is on, this is a storage platform for spare parts. We've got several on the space station, and so that spare MBSU is right up there. So pretty easy access, pretty easy work site. It was only going to take about 2 hours to do this part of the spacewalk. We planned for 6.5-hour spacewalks. That's what we can do comfortably. So this only taking 2 hours means we had 4.5 hours to do other stuff the program needed us to do. Zooming in a little bit more, the only thing holding that box to the space station are those 2 bolts. If you can see them right there. And these are the other MBSUs. They all have just 2 bolts holding them up to the space station. So all we had to do, 2 bolts out, 2 bolts in, we're done, go home, do our other stuff. So how hard can that be, right? So EVA gets started. We got the 2 bolts of the old box out, got the old box temporarily stowed, brought the new box over, put the new box down, got the first bolt in, no problem. Second bolt went in, and it stopped with like 1 centimeter left. And unfortunately, 1 centimeter left is not good enough. So if you don't get it all the way down, you don't get a good electrical mating, and it's as if you didn't do any work at all. So we had to get it all the way down. So what do you do in your garage when that happens? Just torque it a little bit harder, right? So we tried that. That didn't work. So then what do you do at home? Well, you get out the cheater bar and you torque it a little bit harder. We didn't want to do that because if this bolt were to shear, there's absolutely no way we could get that bolt out, and then we would be done forever at this work site, because we don't have a plasma torch or anything else like that to get broken bolts out. So we did the next best thing: back it out, try again, and then back it out. So we backed it out. It didn't quite go down as far as it did last time, and so definition of insanity at this point, we backed it out and tried again, backed it out and tried again, to the point where we gave up after it barely would go in at all. So supposed to take 2 hours. Regular spacewalk duration is 6.5 hours, so 8 hours later. Not so much a happy camper. This is our caution and warning display. So you want that to be blank. That means no problems. Yellow means medium level problem. Red means big problem. So we've got 1 red and a bunch of yellows up there. So not such a great way to end the spacewalk. So we didn't terminate a specific word. We didn't terminate it, but we ended it before getting everything done we wanted to. So we started in a position where the box worked, but we couldn't talk to it. We ended the spacewalk without a box installed at all. So we violated one of the cardinal rules, which is don't make things worse. So we got 6 days to go fix it. I told you it took us 12 months to plan it the first time. We really needed this power box back, and the quickest that we could get ready, turn the spacesuits around, is 6 days. And so we were given 6 days to figure out what to do. So the first thing we did is we went and found the folks, actually the guy, who installed this box on the ground at Cape Canaveral before it launched. And then we also went and found astronauts who had done replacement of similar type of boxes before. These bolts are called H-bolts. It's a long explanation why, but that's what they're called. And there are other boxes on the space station that use H-bolts. And so we talked to astronauts to get some tips on maybe what they did to be successful. So it turns out that when we talked to the guy at the Cape, they did actually have some problem installing MBSU #1 on the ground. It was nothing outside of the limits that were allowed, and so no paper was written on it, but they did actually have to put more torque on it than all the other ones. And then it turns out, talking to the astronauts, that you really shouldn't just bolt it down. What you should do is, these bolts are really sensitive to side loading, and so you really need to kind of wiggle it all the way down so that you get all the loads off of the bolts when you replace them. And we didn't know that, so we didn't do that. I came up with a fancy term for it, so that's dithering is what they called it. So what happened is probably at the ground, before the vehicle even, before this truss segment even launched, they probably created some debris inside the bolt receptacle. And probably wouldn't have been an issue if when we brought the new box in, we had done this dithering thing. But because we didn't, we had some metal-on-metal contact with the debris in there, and that started to jam it up. And we use a dry film lubricant that once you start to flake it off, it comes off really easily. And so that just, every time we went back and forth, we just made it worse and worse. So we pretty much did everything we shouldn't have done, come find out. Okay, so we figured out what happened. We figured out what we need to do, and we figured out what we need to do to actually get it installed. So what we had to do first was clean out those threads, right, to get all the junk out of there. Well, how do you clean threads when you don't have a tap and die set, and you're in space, and you're in a spacesuit, and all you have is the tools that you have on hand? And so we went back to, you may have seen this scene before.
Gene, we have a situation brewing with the carbon dioxide.
We had a CO2 filter problem on the lunar module.
5 filters on the limb.
Which were meant for 2 guys for a day and a half. So I told the doc.
You're already up to 8 on the gauges. Anything over 15 and you get impaired judgment, blackouts, the beginnings of brain asphyxia.
What about the scrubbers on the command module?
They take square cartridges.
The ones on the limb are round.
Tell me this isn't a government operation.
It just isn't a contingency we've remotely looked at.
Those CO2 levels are going to be getting toxic.
Well, I suggest you gentlemen invent a way to put a square peg in a round hole. Rapidly.
Okay, people, listen up. People upstairs handed us this one, and we gotta come through. We gotta find a way to make this fit into the hole for this, using nothing but that. Let's get it organized.
Okay, let's build a filter.
Better get some coffee going, too.
So if anybody who hasn't seen the movie Apollo 13, the guy in the white vest is the flight director. That's Gene Kranz. So they do a pretty good job representing the flight control teams and how they worked, not only back in Apollo, but also still today. But the way that we leverage the flight control teams and the people in our organization is the same thing that you saw in the movie. The flight director tells them what they need to do. Not how to do it, but just this is the solution that we need, and here's when you need it by. And then we have empowered our teams and our people, make them the smartest, and make them exceptional leaders so that they can go dump stuff on a table and figure out the best way, the most ingenious way to solve the problem. And then all they have to do is come back and present the answer. And so we get a lot of things done in a pretty short amount of time because we've developed a culture that leaders are developed at the lowest levels, empowered to lead teams, and then a culture that brings that back to the larger group for integration and implementation. And we'll talk a little bit more about that tomorrow if you happen to come listen to my talk tomorrow. So this is the things that they came up with. And this was really a collaboration of the people that do maintenance inside the space station, the OSO Council, the people that do maintenance outside, so the EVA console, the spacewalking teams, and then the power specialists and engineers and everybody involved with this piece of hardware. So first thing we had to do was clean out the threads, get all the junk out of the threads. We needed a wire brush of some sort that we could just send down there. We didn't have one, so we made one. So we took a piece of zero gauge wire that has multiple conductors in it and just spread it out a little bit and created the chimney sweep. Because when you empower your lowest level leaders, they like to have fun. They have a blast doing what they do, and they come up with creative names for everything. So this is the chimney sweep, and these are those conductors spread out. And this is astronaut Peggy Whitson testing out the design. This is our very expensive cordless drill. And this is the chimney sweep. And this is the bolt receptacle that we're actually trying to work with. All right, so we've cleaned out the threads. Now we needed to run a tap down through the threads and recut the threads if necessary, but basically make sure it's all cleaned out. Turned out there's a computer inside the space station that had the exact same bolt in it that the MBSU had. The computer wasn't using it. We needed it, so we just took it and adapted it to our needs. And again, you're using equipment that was designed for use inside the space station, not for outside, and so we had to adapt it to be suitable for use outside. And that's why you've got zip ties as tether points. You've got tape over surfaces that might flake off in a vacuum. So all your standard hand tools have beautiful nickel plating on them to keep them pretty. That stuff just flakes off in vacuum and atomic oxygen, so we have to cover all that stuff up. But anyway, that's our L-wrench tool that we use to chase the threads. This is what it looked like on the ground. This is what it looked like up on orbit when they built it. And this is a big oven mitt of grease that we actually have up there for lubricating the solar array rotating joints. But it's a great lubricant for external use, and so we used it for this purpose as well. All right, so you've cleaned out the threads. We have actually have a compressed air tool, just like you used to clean off your keyboard. We actually have one that's certified to go outside, and so we took that out with us and used it for its actual purpose. It's maybe the only thing in this whole thing that was used for what it was designed for. And then we needed to get some lubrication down inside those threads, and that's where the toothbrush comes in. We don't have Q-tips, for example, that we can just take out there and swab away inside there. We need to come up with some soft material we could use to apply a lubricant, and it also did a job of getting any fine material out of those threads if there was anything left. So the ingenious flight control team, turns out that the standard issue toothbrush on the space station, the base of it fits exactly into the 3/8 inch drive of a socket. And so they chopped it in half and shoved it in, just like that. And we came up with this tool. And so on the T handle is a spacewalking tool that gives the crew like a corkscrew, right, like a bottle of wine. And you can see that we covered it in grease again. And I don't know if you can actually see the one that I've got. So the one that I've got is the current flight-rated Class 1 toothbrush that we fly, and it's medium bristles, for those who wonder. But it's all curved and pretty, and you can see the one in the picture is actually just flat. It's like the one you get at the dentist for free, right? Thankfully, so this is the latest version that we fly. This was a little bit older version that we flew. Thankfully, because nobody asked us, right, when they changed which toothbrush they fly, but the base of that toothbrush and this toothbrush are the same size, so we can still make the toothbrush tool even today, even though they've changed which toothbrush they fly. And that's important because you would think you have a lessons learned conversation when this is all done, and one of those big lessons should be, we really ought to have a tap and die set that we can put outside. And so that was the action from the program manager. Go fly a tap and die set. Well, to come up with something like that is both safe for use in a spacesuit and also actually going to work outside and capture all of the debris that gets generated and everything else, millions of dollars. So now we have a standard procedure on how to build the toothbrush tool. And we actually did a spacewalk with these H-bolt type box a couple of months ago in January, and we built the toothbrush tool and took it out with us just in case we needed it. So it is now a standard complement of the ISS toolbox. And then, of course, once that's all done, we install it by dithering all the way. And this is just a couple of photos because it's fun to see my friends wearing hard hats of them practicing the dithering. And but to tell you who's all involved, right? So this is one of our spacewalk flight controllers, and this is Drew Feustel, one of the astronauts, and they're just everybody came together to make this effective. And really, we had about 3 days to put this all together before we had to train the crew. And then, again, we had 6.5 hours outside, so we wanted to get this wrapped up so we could go wrap up some of the other stuff that we were supposed to do the first time. And bottom line is that we were able to do that, and we actually got some additional tasks done as well. So the primary one was to get power back to the space station, but we completed some other items too. So it worked out in the end, but in reality, you never wanted to have had the failure in the first place. So there was a lot of lessons learned, conversations that we had about what we could have done and should have done to not get ourselves in that situation. And now we've carried that forward as part of our spacewalk planning, just generically to make sure we avoid those situations. But like I was saying, it's not because I went in and said we need to do this, do that, create this toothbrush tool, create chimney sweep, do it in this manner. It's because we have great teams at all levels that do amazing things. And at my level, we're able to say, this is what I need, this is the time frame in which I need it, make it happen, and they'll work 24/7 until it's ready. And then I can just keep in touch with all the teams that as they're developing things to see how things are going. So just the teams that were involved, we've got a 200 by 100 foot swimming pool. It's 40 feet deep, and I know it's feet, and I apologize. But it's big, and I think it's the biggest indoor swimming pool in the world, and there's a full-size space station in the bottom of it. And so this is the MBSU, and so obviously we're practicing the spacewalk tasks in the pool. This is my EVA officer, my spacewalking officer, with the ground version of the tools, so we could have them on console and talk through the issues. This is the OSO, the Operations Support Officer console. They're the ones that own all of the internal maintenance, so all the hand tools, all the actually the toothbrushes too. So they were huge in making this happen. Sunny Williams, obviously involved as well, and she's celebrating because this is right after the MBSU was installed, and so she's reaching for the stars there. And then, of course, myself getting it all accomplished. So why was it a success? So we had this ingenious creativity. If you're a fan of MacGyver, it's something that he did in every episode. But you plan for failures, and so you fly spare parts. But you also have to plan. You have to plan for the unexpected failure, and train your people to be able to handle them. And part of that is also, large organizations, you've got stovepipes. We certainly do in our operations team as well. So we purposefully teach our people and exercise going across those stovepipes to make sure that every facet of what we're trying to do is understood, and then made sure it's safe as well. And I touched on this, empowering leadership at the lowest possible levels, collaboration, and I've been mentioning pretty much just work that happened in Houston, but it's an international partnership, and so we need to make sure that all of our international partners are at a minimum aware of what we're doing, if not fully invested and engaged in what we're doing. And Aki Hoshide was the other spacewalking astronaut, so the Japanese Space Agency was very much involved with what we were doing with their crew member as well. And the more you collaborate, the more successful you're going to be. It might be hard, but it is a success enabler. I talked about earlier about paradigm shifts and the fact that you can either have them forced upon you, like happened to us, or you can be out in front of it. Sometimes, sometimes you duck and try to hide. Sometimes life happens and you're forced into one, and sometimes you're able to look ahead and find it. So I want to tell you about something we're doing right now that is. I keep forgetting what Ian and John called it this morning. Disruptive industry change. So we are doing that right now. I told you about Space Shuttle, so here's another one. So our primary product is fantastic off-Earth research. That's our product. And everything that we're doing asset-wise is to enable that. That's always been the purpose, but we've, up until 5 or 6 years ago, the real end was just the asset. So we had to assemble the space station, right? And that was our main mission. And if we did some science on the side, then that was great. We finished assembly of the space station in 2011, and all of a sudden it was supposed to be, now go do science all the time. And we didn't really know how to do that. We were in this assembly, fly the space shuttle, build the spacecraft mindset. So even though we were trying to do science, we were still trying to manage it like it was an assembly mission, like the asset was the most important piece instead of the bottom line, which is the science. So we're currently going through this entire new initiative. It is very disruptive, and it's from the top, which is at the program manager and even at the agency, all the way down to the individual researchers, engineers, flight controllers. And we're talking about it's a culture change, and it's a philosophy change, and it's process changes. And what we're trying to do is streamline the process and the timeline for getting science to orbit, doing that science, and then bringing it home. So we're changing everything that we do with respect to space station so that the researcher and their science is first and foremost. And then almost secondarily, we're making sure that the facility is up and running to support doing that science within the aspects of keeping the crew alive and safe and healthy because they are in low Earth orbit. So just to give you a non-industry example of going through disruptive change, yeah, we're definitely doing that, and it's painful and it's a long process, but it will be definitely be rewarding when we're done. And then I like my last bullet mostly because I've never seen that many iddies in one bullet before, but that's what we try to do. So I'll let you ask questions, but I've talked a little bit about Space Shuttle, and unfortunately I used to be able to say you should really go see a shuttle launch. That's not possible anymore. So I want to show you a video of the first 2 minutes of a space shuttle launch, just to try to give you some perspective on what it was like to ride that amazing vehicle up into orbit. It's the first 2 or so minutes. And a couple of questions one question people usually ask me, so I'll just tell you, in the first 10 seconds, a bunch of stuff falls off. It's supposed to, by design. And then if you're an aerospace engineer, you'll get really excited around 750 miles an hour, because that's when we start going, from 700 to 800 miles an hour, we start going transonic, and then we go supersonic. And so watching you go through that transonic regime makes me excited, so hopefully at least some of you think that it's cool too. So I'll show you that, and then we'll do questions. That's the space shuttle flying away. So it's pretty cool. In 2.5 minutes, or a little bit less than that, We went from 0 to 3,000 miles an hour. We went to 0 to 100 in about 10 seconds. You cleared the tower in 6 seconds. But you need 17,500. So in 6 minutes time, more or less, you've still got 14,000 miles an hour you need to gain. So at this point, you've just barely gotten out of the heavy atmosphere, and now those 3 engines that are left on the orbiter go into full gear, and it's an amazing ride. They have to throttle back just so they don't overload the astronauts. Anyway, I go on and on. I love what I do. It's an amazing thing, but if I don't let you ask questions, I'll get in trouble. So,
do we have any questions? There must be. Where's Glenn Green? He's just absolutely jealous he hasn't got one of those in his fleet to look after. There's a question down.
How long did it take to build?
Wait.
How long did it actually take to build the station?
It depends on how you want to say building it. Some would say we're still doing it. Assembly complete was officially designated as in 2011, when we brought up the last major component with the space shuttle. So that's assembly complete. But there are actually some Russian laboratories that are still on the ground that haven't been launched yet. And then actually, so I mentioned the SpaceX is going to fly on April 8th. They're bringing up an inflatable module. So technically it's research, but it's going to be, it's like a big balloon that the idea is that you can make inflatable modules so they're compact when you fly them. You blow them up, and then you can have a much bigger space. And so there's a company called Bigelow that is working to create space hotels. And they're going to be inflatable modules, and so this is a smaller version to do like a demonstration. So we're still adding to it, and it's a lot like Tinker Toys. For those of you who know what Tinker Toys are, we can actually move stuff around if we wanted to. So.
You hear a lot about space junk flying around up there. How does the space station handle that? Is it above it or whatever?
We're in the thick of it. So space junk is our #1 risk. So there are officially designated, I'm sure you all have this too, right? A risk management system, and you've got your top risks. So our #1 risk with space station is MMOD, micrometeoroid orbital debris, which is a fancy way of saying space junk. So the way we handle it is that the pressurized modules are shielded for anything smaller than 1 centimeter. The equipment that is outside is, some of it is protected, some of it is not, and so that's somewhat of a risk that we've accepted. And the Air Force can track objects that are 10 centimeters or larger. So clearly there's a gap of 1 to 10 centimeters, and that is why we have the risk. Because if something does come up that we can't track and it hits us, it will penetrate, and depending on the hole size, either we can find it and repair it, because we have equipment on board to do that. We can find it by isolating a particular laboratory and lose that laboratory. So that's what happened on Space Station Mir. When the Progress vehicle hit the Spectre module, it was too big to repair, and so they closed off that module, and it was just permanently lost. And then if it's large enough, we have to actually evacuate. As far as the scope of the problem, it was bad a few years ago. The Chinese did an anti-satellite test with a missile or a rocket, and blew up one of their own satellites, and just, I don't have a chart here, but if you look at orbital debris numbers, it just goes straight up with the amount of objects in the sky. And it's bad for us because it's actually around our orbit a little bit. It's higher, so all that stuff is just raining down through our orbit. So it sounds really dire, but it's also big sky theory comes into play too. So it is a very big space in low Earth orbit. And so we manage it that way too. So the way we actually manage orbital debris is we have we call it a pizza box, but it's some airspace around us that if anything's gonna come into that space, we get notified, and then we'll decide what the probability is of that happening. And if the probability is low enough, we'll actually do a small burn of the engines on the space station to change our orbit to make that probability go away. So.
In your lessons learned, Ed, have you revised your toothbrushes in flight inventory?
and or have you got an astronaut with dirty teeth?
Yeah, so that question, it sounds funny, but that question actually came up when we did this for the first time, right? How many do we have left? And then to get ready for the spacewalk in January, we actually had them do an inventory of how many toothbrushes they had to make sure that we didn't get into the dirty teeth situation. So we maintain just enough. That gets back to skip cycle planning, right? Everybody's supposed to change their toothbrush every 6 months, right? So we all do that. At least that's the guidance in the US, I don't know. So there's more than enough to supply that. We don't actually fly additional ones for this purpose. We just steal somebody's and then resupply it.
Thank you very much, Ed. That was an excellent presentation. You've taken us through, well, a lot of the challenges involved in a low Earth orbit of a space station. How much bigger of a challenge is something like a manned mission to Mars in comparison to this?
So it depends on what topic you want to address. So if we talk about resupply and maintenance, it's easier and harder. So the easier part is you don't have much in the way of options. So it takes 6 to 9 months to get people to Mars right now, and you can only launch every 2 years to Mars, ideally. So you would pre-supply. So you would send supplies in advance of the mission in a 2-year window, and then get everything operating on the surface, and then the next 2-year window you would launch your crew. So presumably you would land a lot of supplies on the surface, and then you'd probably have a much smaller crew capsule with a habitat, nothing nearly as large as what was in the Martian. And so they would really have with them only the resupply that they need for the transfer vehicles. So it's easier in that perspective. You're not continually doing resupply like we are with space station. The hard part is you have to plan in advance for every failure. What are you going to send? And I'm absolutely certain as soon as the people get on their way, we'll realize that we didn't send something that we needed. And so that's when you really need to have adaptability in how you're going to manage things. And that's why we're doing research like 3D printing and additive manufacturing. Can we do that reliably in space? What are the material properties still going to work the way they do on Earth? Can we rely on the products? Right now we're doing it with plastics, which really won't be all that helpful in a lot of cases. And so as that industry matures, then we're going to start doing it needs to be really small and lightweight, and then see what we can do for building electronics and even food, because that's actually food and water is going to be probably the heaviest thing that we fly. So there are lots of answers to your question. It just depends on the topic that we pull on.
G'day. On the computer systems on what size processor do you have? Because we always hear the myth stories that we have more processing power in our pockets. And how do you go about protecting it from solar flares?
So there's 2 answers to your question regarding processing power. The command and control brains of the space station are radiation-hardened chips, and that makes them probably antiquated in today's terminology, but early 90s technology. There's some amount of, they have solid-state drives, so that's pretty cool. That's relatively newish. But the whole internal communication system at the command and control level uses a 1553 military standard bus, so it operates at 1 hertz, so it's really slow and it can't actually carry a lot of information. So we actually have a totally separate system for our research that uses a 10-base-T Ethernet, which again is old and slow, but it's much better than the other system. And we bring all that data down through a separate channel at 300 megabits per second, and we're working to upgrade to 600, so we're trying to keep ahead of technology in that regard. Since the main computers are also slow, we actually use a lot of laptops on the space station. We usually have between 100 and 150 laptops deployed at any one time. We've got 6 different LANs on the space station doing various things. And they're off-the-shelf laptops, which makes them easier to replace, but they're also susceptible to radiation hits. But they're laptops, so when things go cattywampus, you just reboot them and you get on with life. So it's not a big deal usually. I think I answered all the questions.
Hi, thanks. I just wondered, you said that it came as a bit of a surprise when you lost the shuttle, and you've now got, I think, 3 or 4 different launch platforms. Have you considered what you may have to do as a next step for that?
So what we're doing now is our biggest concern right now, that ever since the shuttle stopped flying, we've only got one way to get people up to the space station, and that's on the Russian Soyuz. It's an incredibly reliable spacecraft and a rocket, but as you saw with the progress, even incredibly reliable systems can fail. And so we don't have dissimilar redundancy right now for getting people into space. And you know, you'd say, well, just don't fly them until you regain that capability. But in our case, we're always going to have people up on the space station, and we don't want to just leave them hanging out there for forever. And actually, the Soyuzes have to come home after 210 days. Just that's their certified lifetime. So that's their lifeboat. So if the lifeboats have to come home, so do the crew, and we don't want to leave the space station untended. So we're working on a commercial crew capability where SpaceX and Boeing will actually have capsules that they'll launch from the US to take crews up to the space station. And that's our real focus in the near term, is to regain that dissimilar redundancy. Astronauts and cosmonauts will fly on all of these vehicles, so it's not like a US only, Russian only thing, but we'll have multiple options for getting up to space station again. Further out, we're transitioning as much as we can to that commercial sector so we can focus on going out to that next destination with the Orion capsule. So that's what our main focus is as far as development, is Orion and then the big rocket that we need to go back to the moon, cislunar space, Mars, and beyond.
A very interesting presentation. It was really good. My question is, you talked about supplies going up, and you know, we're human beings, and in 6 months we you know, need to go to the toilet occasionally. So what happens to the waste products in the space station, and what risks do they represent?
So solid waste gets, so first of all, the toilet facilities are a lot like a camp toilet. So solid waste goes into a individual bag, and then you tie the bag off, you shove it back into the bottom of the can, and put a new bag on for the next guy. And so that's how solid waste goes. We don't really do anything with it other than close it up tightly when the can is full and put it in one of the cargo ships departing. So the SpaceX vehicle can return actually to the ocean. Every other vehicle burns up in the atmosphere, and so we dispose of it with our trash. Liquid waste actually gets reprocessed. So we have a urine processor and a water processor that'll take urine and then also sweat and condensate and put it all together and recycle it into drinking water. So we actually reclaim about 90% of the liquid water on the space station for consuming. So the astronauts like to say that they'd like to turn yesterday's coffee into tomorrow's coffee. But that's a whole, water management on the space station is an incredible, it's a thesis that you could do for PhDs. It's amazing. So water's a very precious resource.
Ed, that's absolutely fascinating. I'm going to sadly bring this session to a close, and we'll use you as a draw card for outside in and around Speaker's Corner with a beer. It sounds like a great topic. We started the day making cash from dirt, and we've ended the day fixing a space station with a toothbrush. Ladies and gentlemen, please thank Ed very much for his presentation. Ladies and gentlemen, the doors are open. It's party time now. We're all finished for the day. Don't forget that assessment. Let's enjoy ourselves. Please stay around. Drinks are on TWM. Thank you very much.